Now I invite Sri Tulsi Madam to introduce Dr. Ram Soorat sir, resource person for session 2.
Good evening, everyone. It is my privilege to welcome you all to today's session. I feel truly privileged to introduce our distinguished speaker, Dr. Ram Soorat, Sir, Assistant Professor at the School of Technology, Woxsen University. Sir earned his PhD in physics from the University of Hyderabad, specializing in quantum optics, and he brings extensive expertise in quantum information, quantum cryptography, and quantum technologies. His research covers some of the most advanced areas in the field, including quantum random number generation, quantum key distribution, quantum teleportation, and quantum error correction. He has also published extensively in reputed peer reviewed journals, contributing significantly to the advancement of quantum science. Before joining Waxen University, Sir had held research positions at leading institutions such as Shivnadhan Institute of Eminence and the Indian Statistical Institute, Kolkata. Sir also served as chief scientist in Abu Dhabi, where he developed pioneering protocols in quantum communication. Beyond research, Dr. Surath Sir is well versed in tools like LabVIEW, Python, and Qiskit, reflecting his commitment to bridging theoretical knowledge with practical applications in the rapidly evolving field of quantum technologies. Today, we are fortunate to have him share his insights on quantum random generation. Okay. Ladies and gentlemen, please join me in extending a very warm welcome to Dr. Ram Surat sir. Sir, we are honored to have you with us and we look forward to your lecture. Over to you, sir.
Okay, so I'm really sorry for this interruption. So yeah, already you have heard about me. So this is my contact email. I mean, after this talk, if you feel that need to do some collaborative work, so you can contact through my this email, and this is my Woxsen email ID. Okay, so today I'm going to discuss about quantum random number generation. So in that case, first, what is quantum random number? Where we need to generate this quantum use we are going to use this quantum random number, and how we are going to generate. And already there's a lot of method is available in classically. Then why this quantum random numbers generation need to be explored. So let's have one example here. Just like already you know that communication. So I used to call this quantum communication. Why? Because that we are using here quantum random numbers, so that's why I'm calling it quantum communication. So in that case, for communication, you need at least minimum two objects. It's more than that, three, four, five, like that, and they are connected through some medium like either it's a free space or fiber space, fiber. So the basic idea is that here, actually, what we used to do that if suppose you have a message, some message, let's say the region, for example. So instead of sending this actual message through this, I mean, to communicate to receiver from transmitter to receiver, we are sending some random signal. We are generating first a random signal between these two parties, transmitter and receiver. So if we generate a safe and secure way, this random signal, then only whatever information is there that we can send from one place to other place safely. So we generate here this key. We used to call this random signal between these two parties, transmitter and receiver, first, and then encrypt the message here, message and key, this encryption. So instead of sending this actual message, we are sending this encrypted message. And once this key already has this receiver, once after generation, so this encrypted message, and they'll decrypt this one, then you will get a actual message. So this is one of the example that where we are using this random signal. So this is very, very important. And now, I mean, wherever security comes in the picture, whenever you need some secure, things, then you have to need this quantum random number generation. So I'm going to discuss here basically two different methods to generate quantum random number generation, and we'll see from scratch to their theoretical concept and experimental visualization, then post processing analysis, and then final is actually a niche test, and all we are going to learn in this presentation. So apart, I mean, here now there is several companies involved in this generation of quantum random number generation. Like ID Quantiq, this is one of the leading company which is working in quantum technology, and they have most of the quantum, you know, related hardware stuff like QRNG. They have QKD setup, and also means if you look in some other part, they are actually leading company in this quantum field. Then microphoton device they are also generating this QRNG, Pico Quant, QR. We'll see here. There's a several company here, and nowadays if you want to use online QRNG, then these are the service provider, like this Quantum Random on Demand, University of Geneva, Australian National University, and Hamburg University. So they are actually generating. Even nowadays, some more also added here. So let's look at some hardware, that how it's look like. So this is the hardware part, which is from ID Quantiq. So they have like here legacy quantities, that is 4 Mbps, and if you put 4 more here, so it becomes 16 Mbps. So that this is PCI based, and that you can see their cost also. So this is actually somewhat costly here. So this is the random hardware based random number generation from ID Quantiq, and this is going up to 16 Mbps, and this new quantities QRNG, that is going PCI based, that is for 40 Mbps, and another one is 240 Mbps. And we can see here some other companies also like PicoQuant. They are going generating like 150 megabit, and their quantum random number generation is based on the photon arrival times. Then here some other devices is there that they are using different methods. We'll see here how many methods is there in coming slide. And in 2021, I guess, in 2021, this SKT, South Korean technology, and Galaxy, the Samsung Galaxy, they jointly came up with this mobile phone, which is Galaxy A71 5G, which is using actually quantum random number generation. So I mean, this phone, we can say that this is very safe and secure way. That is, this phone itself can generate quantum random number generation. Okay, so we have seen here that how companies involved in generating random number. In India also, there is some few companies they have work on this, like Kino Lab is one of the leading one. So yeah, and there's a lot of research going in India as well on quantum random number generation. So before going to that, let's discuss what is random number. So random number is like unpredictable outcome. So for example, let's tossing a coin or a dice. So what are the probability? These are actually basically this is, suppose you toss a coin, so you don't know whether it's going to be head or tail. So it's a kind of unpredictable. So if you collect the like 100 sample or 200 samples, so it's actually the collection is will tell you head tail, like, so it's a random sequence. So there's a two types of random number. One is pseudo random number, which is deterministic process, and that is based on algorithm we used to generate by software. And second one is hardware based random number. So the problem is this software based is that based on the sequence, now we can write, we can predict the algo, what is the algo behind that one. So that's why it's not safe and secure, pseudo based. Because if I know the algo, I can generate I can predict the next outcome. So this is the dangerous, which is actually nowadays most of the random number which is coming, we are using as a OTP and all. That it comes from pseudo random only, software based, that is based on some algorithm. But I'm sure that this is not going to be happen, I mean, for longer time. Definitely is going to be cracked down by once quantum computer is actually working on that one. So here the second one is hardware based random number. In this hardware based random number is also there are two types of random number. One is deterministic, which is deterministic here is basically what is happening is that after some time, some interval, let's say suppose we are using some thermal noise or blunt photo noise or atmospheric noise. So what will happen is after some time it's repeat their own path. So this is what this we used to call deterministic. But non-deterministic, that is actually comes from the quantum behavioral nature. So once we have any system which is following quantum rules and regulation, and we measure the system, the same system, it will give you always probabilistic outcome. It's every time it will give you different outcome. So that's why it's we used to call this non-deterministic, where the quantum phenomena involved in that. So in this one, there's a several method is there. The optical path generator, time stop error generator, photon counting generator, attenuated pulse generated, generator based on vacuum quadrature, generator based on phase fluctuation coordinate, and the generator based on amplified spontaneously. So there's a multiple method is there that we can generate quantum random number generation. So here I have chosen two different types of generation, which is first one is vacuum quadrature and second one is phase fluctuation. And the reason behind this one is that vacuum quadrature, when you need like slow process, then we can go for vacuum quadrature, and when you need generation like in gbps, then we have to use this phase fluctuation. For mbps, vacuum is enough, and if you need in gbps rate, then you have to go for phase fluctuation. So this is why I'm going to discuss about these two different types of quantum random number generation. So here the next one is actually this is the like kind of research survey that which is I told I have shown this multiple types of generation. I mean generation is there, and based on that their rate and what are the challenges is there. We can discuss on this one later if you are interested in this one. And here is the companies involved, and they are targeting like photon arrival 100 mbps like that, gbps, and this is quantum lab, then case quantum security, id quantiq. So I told that id quantiq one of the leading one in this area. So this is for that. So here random number simulation, you might have used this one. So for that we used to write this code, like suppose we are simulating some game up there. So this is the code we can write in python, and it will give you some random outcome. I mean, if you can write it, and based on that you can you know play a game. So here the and for this OTP generation, we need like this one-time password, basically for authentication and security purpose. So we can generate this one based on this. So I'll show you in the next slide here that this is the software based. Actually, this is pseudo random number generation. I'll just a minute. I'll put it in full mode actually. Okay. So yeah, okay. So this suppose we have some algorithm here for pseudo random number. Let's say xn plus 1 equal to axn plus b mod n. So in this algo, as per our requirement, we can generate this random number. Okay, let's say I want to generate between a number between 0 to 5. Okay, so in that case we can choose here some some value here, a value that is fixed, b value is fixed. We can keep changing this n value. So based on that, means this one. So let's, for example, let's, if suppose I have chosen here a equal to 1 and b equal to 1. So what will happen here is that if you put here n equal to 1, uh, n equal to 0, so x1 will give you here x0, I mean initially we can put here some x0 is 2, so 2 multiplied by 1 plus 2, so it's a 4, 4 mod 5 is 4, like x2 is will give you 1. So this is how you can generate the random sequence with from 0 to 5. And if you want to generate a random sequence between 0 to 6, like for dice, so here, so you can just change it, put it this mod 7. So every time it will give you some random sequence. It keep changing this n equal to 1, 2, 3, 4, 5, 6 like that, and you will get every time you are getting here some different types of random number. So this is what nowadays we are using some algorithm and generating this random number. So for OTP, for any type of game where we are playing this. So this is one of the ways to generate this software. So this is we used to call pseudo random. So now we understood that what is software-based random number generation. Now we are moving towards hardware-based random number generation. In hardware-based random number generation, we are going towards non-deterministic. Non-deterministic because we are going to use this quantum phenomena in this. So in this one, the important thing is that selection. I have shown the different types of scheme is there, like photon arrival, phase fluctuation, vacuum fluctuation, like that. So first you have to choose the scheme. Second one is the process. What is the post process after once we get the raw data from this setup? So that raw data is not directly useful. We have to make it like we have to refine that data and then do the statistical test. So that test will tell you whether this generation, whatever outcome is comes from that is useful or not. We'll see here in next slide that the first one I'm talking about the QRNG based on vacuum quadrature. So when we are talking about this vacuum, what do you mean by vacuum? Vacuum is it's like nothing. Nothing means we used to call in quantum that is 0 point energy. So that energy we are going to harvest. How we are going to harvest? By using this homodyne detection method. So homodyne detection method is that we have a laser here and we have a beam splitter. We can call it this 50-50 beam splitter. So this laser beam is coming here and it divided into two parts. 50% light goes here, 50% light goes this side. So this is a homodyne detection. We used to call this is homodyne. So ideally, what we see, if you look at this is 50% intensity here, 50% intensity, and if we subtract this, what will happen? Ideally, we used to get 0, but actually, what is happening? We are not getting 0. Why? Because of the another port. We are assuming that there is some energy which is vacuum. It's ground state energy actually going in this side. So this going inside here, this ground energy divided into two parts here actually, and then because of that, as normalized condition, we are getting some kind of fluctuation. So we consider that we are harvesting here 0 point energy or vacuum, and that vacuum is actually we used to call in quantum in nature. So if it's a quantum in nature, so if we measure every time the same system, then always we are going to get probabilistic outcomes. That probabilistic outcome is actually nothing but our random number signal. So these are the references. You can go through that for more detail in this one. Even I'm going to discuss about this one. So in this case, what I have done is that we have used this laser, that is 780 nanometer wavelength, and this is a polarizer here. Hubble plate to actually turn this light into a 50-50 beam splitter. So we actually using here Hubble plate here. And this is polarizing beam splitter, because normally if you are using this normal beam splitter, then it's difficult to make it 50-50. So it says that 50-50, but due to extension ratio and all, there's a other parameter is actually it's not 50. That's why we are using here polarizing beam splitter. And here there are two detectors, similar detector. We in our case we have used APD 130A2 by M, And of course, to operate this laser, we have used temperature controller and laser that controller. Okay, that is from, and one oscilloscope here from Tektronix. And this other item is actually basically from her labs. So this is what we have done in our lab. Well, I was doing I was leading as a chief scientist in Abu Dhabi. So that time we have done this one. So this is the schematic diagram. This is how it's look like. This is laser, then lens, calling it the beam, and then polarizer, and then here this beam splitter, and there's a detector. Two detectors here. So this is another way of this representation. So what happened when we have seen here this, once we look at this signal here, outcome here. So this is LO1. LO signal is actually electric noise. Electric noise is what is I'm calling it here when there is no light falling on this. Okay, so when laser is off and we have collected this signal, and this is some noise is coming. So that is electric noise. That is, the photo detector is sensing something which is so we used to call it background noise also. And this red signal is basically our vacuum quadrature. Okay, so once this 50-50 beam splitter is there and two similar detector is there, and we subtract this one, then we used to get this red line, red signal, and this blue line is basically local oscillator quadrature. So in this is just like add those signal I1, let's say this is I1, this is I2, so add this one, so you will get this local oscillator. You need to normalize it, then you will get this one. So if you plot this histogram of this signal, so it look like this. This is a Gaussian actually, basically. So once we have a Gaussian signal here, so Gaussian distribution is tells about that whatever outcome is there, that is random. It says random, but it doesn't mean that you are going to use that one. For that, you need to do this niche test. I'll discuss this one, how we are going to this. So we plot this histogram of the signal, this electric noise, vacuum quadrature, local oscillator quadrature, and we can see here this is the histogram is actually basically is look like Gaussian fit. So we have collected signal for 1 mega sample and 2.5 mega sample. Both are actually look like the same here. This blue one is just behind this thing. So once we have this now data here, this is called raw data. Now we need to post process this one. So before going to that, just I would like to discuss the theoretical concept of this one. So here we consider the vacuum state, which is represented like this, zero state. It's in ket notation. We used to write minus infinity plus infinite. And this sin x, this is how we used to represent, right, in quantum signal. So this is wave function for zero, vacuum state, where x is amplitude quadrature, and here x and x naught is equal to delta x minus x naught, and psi is the. So here the measurement of amplitude quadrature collapse the wave function into quadrature eigenstate, giving the associate outcome unpredictable. I just follow the Gaussian predictable. This is what I have just now I talked about this. Once you measure this one, this collapse, and this gives you unpredictable outcome. So, and this is following the Gaussian distribution. So before that, this beginner function. There is a beginner function. Beginner function is actually this allow a direct visualization of quantum state as a distribution over phase space. So here, this is how we used to write this beginner function. This is beginner function xp, and this is the method. See, in this one, if you want more discussion and all, I have all the information about this one. We can discuss after this meeting also. So beginner function for given state we can write here this one dx, and that should be one. So here we are going using this Wigner function. Here Wigner function for vacuum state in phase space is written like this. So this is actually basically what is minus x square exponential. This is basically telling the Gaussian nature. So if you look at this one, so because this is Wigner function is giving you direct visualization of quantum state. So that's why we have checked this Wigner function, and here this Wigner function versus this we found is the Wigner function quadrature clearly showing here this Gaussian distribution. This is our result actually, basically, and that is showing this perfect randomness. So in this one, what happened that we have here this local oscillator and vacuum. Okay, if you look at this here, this is laser. We used to call this a local oscillator, and this is vacuum state. So these two are input here. So we can theoretically we can model this. So what we can see is here that this is local oscillator. This is alpha LO, and there is some fluctuation part is there. And this for vacuum, there's it's start from zero. Okay, we used to call it zero. So is uh, here this is our you know hello hello
sir.
please uh, okay. So in this case, so this for vacuum there's no, I mean, we used to consider this as zero, so this is fluctuation part here. So if we look at the current part in this one, this is delta I square. Delta I square is, one is I1 minus I2. So because we have a two detector here, this is detector 1, detector 2, so we can call it here I1, this is I2. So that fluctuation I1 minus I2 is delta I. Delta I square, if you look at this one, then what will happen is after solving this one, you will get some portion, this is time delay here. Okay, so delta square e by tau into I bar. This is, so if you plot this one between delta I and I, you will get some graph like this. So basically, this is talking about this photocurrent is directly proportional to quadratic amplitude of local oscillator. So this is actually, this is kind of evidence which is going towards vacuum quadrature and how to measure this theoretically proof here. So at this case, we have seen that theoretical observation, experimental observation. Now we have a data. Now we need to do the post processing. So in post processing, the important thing is that, of course, there is several steps involved in that. But now I'm talking important. What I consider is minimum entropy ablation after a random number, and then application of randomness extractor. Okay, under random number, uh, Topless has extractor. I'm going to discuss here. So we have a like raw signal which is following the Gaussian distribution. How we are going to convert this one in terms of 0 and 1 information. So it's like if we are using one bit like 0 and 1, so we can divide this Gaussian. So half portion, if from here is whatever signal is coming, that is 0, from here this is coming 1. And if we are using 2 bit, so there's a 4 combination, 2 per 2. So this area, when signal fall in this area, this is 0 0, in this area 0 1. Here this is 1 0 and this is 1 1. And if it's a converting, we are using like let's say 3 bit. So 2 power 3 is 8. So this area, this same graph, but it divided into 8 different parts. Okay, so this is, we used to call this bin size. Okay, so we can convert our signal from 0 into 0 and 1. So either in 2 bit, 1 bit, or 2 bit, and 3 bit, like that. So of course, if you go for more bits, then your accuracy is going to be down. Okay. So here, first we has to discuss about, I mean, how to calculate this entropy. Okay, minimum entropy. So for minimum entropy, this formula is H equal to minus Mason I equal I tends to n pi log 2 pi. So here, if let's say n equal to 2 power n, where n is the ADC bit. So what we are doing here, this we are calling here binning. So now we can call this one ADC bit also, 1 bit, 2 bit ADC. So if it's a 2 bit ADC, okay. So here n we are taking as a ADC. So it's a 2 bit to 2 power n means total is 4 combination, that is 0 0 0 1 1 0 and 1 1. So let's say we have some sequence like this. We have chosen some random sequence, which is this is random, and we are calculating this 0 0. Okay, so how many times we are getting here 0? So P0 is, if you are looking here 2 2, so 1 2 3 4 5. So we don't find 0 P0. Okay, there is no P0 here. So P0 is 1. 0 1, so 0 1 is 1 2, so there is a 2, so total is actually 5, so 2 by 5. So p 1 0 1 0 is 1 2 3, so 3 by 5, and 1 1 is, it's not showing, it's a 0. So you, if you, for this sequence, if you do this entropy calculation. So what will happen is P0 0, this is 0, this is 2 minus 2 by 5 log 2 by 5 minus 3 by 5 log 3 by 5. So calculate this one, so you will get this H equal to 0.966. So if entropy is like near to 1, this says that this is a really very good random number. Okay, so for our case, what we have generated through hardware base, we have this is ADC bit here. So 1 bit, 2 bit, 3 bit. So for 1 bit, it's supposed to be like it's nearby 1, so this is very strong. For 2 bit, it's supposed to be 2, but when we are using 2 bit ADC, so in that case, it's low actually. In 3 bit, it's supposed to be 3, but this is low, it's 4. So I told that if you keep increasing this winning size here, the ADC bit, then your randomness will decrease basically. So this is not a very good random number in that case. So 2 bit is promising, even 3 bit also we can go, but 4 is actually much, this is not good to use. So once we calculate this entropy, then we have to go for randomness extractor. So randomness extractor is, first I'm talking about this one element extractor. So what is happening? Suppose one element extractor, what it does is that suppose we have a sequence like this, 0 1 0 0 like this one. So first it's here, this is the method they are using. So wherever 0 0 is there, 1 1 is there, discard those things. And wherever 0 1 is there and 1 0 is there, 0 1 is converted to 0 and 1 0 is converted to 1. So here, this, after this much big sequence, if you uh, apply this one element extractor, then what will happen? 0 1. So 0 1 is 0. So we'll put here 0 here. 0 0 is discarded. 1 1 is discarded. 1 0 1 0 is 1. So here 1. Again 1 0 0 1 0 and 0. So 0 0 1 1 is discarded. 0 1 is converted to 0, like that. 0 0. So we are actually basically what we are doing there, we are purifying this whatever our random signal is there, raw data. So by using this one element, this is how one element extractor work. The second is we are using this Topli's hashing extractor. Topli's hashing extractor is, what is doing is that mathematically is if you put any value of this in this one, it will give you a fixed amount of outcome. So let's say, for example, if you pass through this, let's say I'm talking, writing this quantro. So this is something like 64 character you will get. And if you write here, quantro is a quantum optics space R&D company. This is still is giving you 64 4-bit character. So like that, this, what will happen? No matter whether it's a small or big, it will give you a fixed amount of length. So here, what we have seen that we are getting, I mean, from big length of data to small length, but here we can compress or we can increase the data here using list of rich hatching structure. So how this is mathematically how it's work, that this is top list hatching matrix and this is raw data, and once you apply this one you will get some this kind of outcome. Now once we have this random signal which is now like raw data, and after extractor we have a refined data. So if we do the autocorrelation for raw data, so this is going nearly 10 power minus 2. So and here autocorrelation after this raw data after top page has an extractor, what we can see is that it's going uh, near 10 power minus 5. So means whenever our autocorrelation is going towards more towards 0, then means is talking about that there's no connection between neighbor point. This is what this autocorrelation is talking. So this looks like somewhat promising. We'll see some other thing also. Then once we do the autocorrelation, then we have done this bit. We just calculate the bit rate here. So there are two different method to calculate bit rate. Either you can go after post processing, bit rate is sampling rate into ADC bit. So bit rate is here, and this is number of bit. We used to call this ADC bit. Or we can directly go through sampling rate into entropy. So both method is valid here. So here we can see is that for one, this is actually basically our raw data, and this is our after correction of this one. So we can see here for 2 bit. So if you multiply by here sampling, this bit rate is something going like a 0.8, or if you 3, so we can go qualify 1.4. So actually this is not the only method which is going to be like that is affecting our generation rate. The best part is that it depends on our bandwidth of detector. So detector play a major role in this. So once we tested here, so then we go for this random test. Whatever we have the sequence, this random sequence after 1 mn entropy extractor and propylase Helsing extractor. So this is the random test we used to do. So there are multiple types of tests available. So authentic one is we used to follow that this is NIST, which is Nestle Institute of Standard and Technology, and die hard is there, the pi test. There is multiple tests there. So I just follow this NIST test. So in this case, this is a software based actually basically, so you can just download from this website, and these are the commands sudo for update gcc and give your file detail. It will take it and that random sequence, and after that it will generate some 15-16 different types of outcome. So here this is the outcome from this niche test. So this is we used to measure this one using p value. P value is has some threshold 10 power minus 2. If it cross this 10 power minus 2 p value, means that test is passed. So there is 15 different types of test: frequency test, block frequency, cumulative sum, run, longest run, like that. There is 15 different types of tests. So at a time you can test all these 15 tests on this our refined data, and we can see here this is pass all the tests. So if we are doing before extractor, this will not pass. Some of them definitely are going to be failed. Okay, so this is for this niche test. So while I was working as a chief scientist, so we have done this one, and we have moved towards making integrated module, chip module. So this is the chip module, how this is looks like. uh, this is what I have discussed. Those component is there on this one, and somehow this could not proceed further. So here there is some limitation in the physical random number. if the system is sampled at high rate, there's not enough time for system to change the random number as not independent. And these are the difficult limitation. It is difficult to give convincing argument of randomness of the adding external device is usually inconvenient, failure are difficult to detect. Official recommendation suggested introducing startup test and total failure test, online test and check error during operation. So of course we have to take care several part of that. But good. So this is what I have discussed about quantum random based on vacuum quadrature. Now the next one is when we are talking about we need this high speed random number. Okay, so we have to use this another method, that is phase fluctuation. So as we know that phase is very difficult to catch that. So we cannot detect the phase because this is very fast. So in that case, we are uh, capturing the intensity due to phase fluctuation. So how we are going to do it? This is the experimental setup. It's a very simple Michelson interferometer setup. So what is happening? This is the laser here, and again this is we can remove this lambda by 2. It's not needed. So instead of PVS, we can put here VS. So 50-50 beam splitter, let's say, and there's a mirror here, one mirror, and there's another mirror here. So light goes here. Transmission light is fall on mirror, it will get reflected, and it will go partially this side and reflect and go this side. And another one is 50% light goes here, reflect, and goes some portion here. And so basically at this point, we are getting two different of light, two beam, one from this, other from this. So we are getting two, light here, two beam here, and both are having coming from same source, and they are coherent in nature. So definitely they are going to interfere. So once they interfere here. So due to this interference, we used to measure those things. To get this quantum random number, we are going to operate this laser basically at some threshold point where stimulated emission is spontaneous emission is dominating stimulated emission. So, and actually that is what is called at that particular point we used to say that most of the signal is quantum in nature. Most of the signal, it's not fully. I'm clarifying here. So that is we are going to find out that at what are the current we are going to operate this laser where we are getting here this signal here random, and that is in quantum in nature. Okay, so for that we have used this same laser source 780 nanometer wavelength, and in this case we have used lambda by 2 PBS, lambda by 4, lambda by 4. There is two mirror. These all are from Thor Labs component, and there is one detector here. So in this phase fluctuation, the biggest role is playing this detector. If we have a high bandwidth detector, we can go up to like maximum speed of randomness, like in GBps. Okay, so here we have less. What we have used that is less bandwidth. So accordingly, that I will show you that how randomness behave collectively. And for more information, these are the references you can go through that. Okay, so in this case, here this theoretical formulation is that we are using this CW laser. So electric field can be represented here E equal to E naught e power minus I omega t plus theta. Okay, so this is well known. I hope you know this one. And if you calculate the intensity for this one with delay of tau, okay, then we can get here. I mean, E, and we can take this conjugate of this one, so that is intensity. So you calculate this one, then you get here 2 E naught square plus 2 E naught cos omega t plus uh, t tau. So to measure the signal can be described here. here I interested that that is the 50% power of this one. So we use this one as a power P cos omega t plus this one. So if we have a choice, we can put here omega t equal to 2 m pi plus pi by 2. Then this will reduce here I equal to that intensity directly proportional to P sine theta T and tau, T of tau. Okay, so this is just some theoretical proof of this one. So based on this one, we are going to calculate some parameter where we are going to get our signal in quantum nature. So first, we have to calculate the variance. Okay, so in phase fluctuation, we can write this variance, total variance, that is theta t tau mod square is equal to q by p plus c. So here, this is total power p, this is quantum, we used to call quantum signal, but this is classical nature. So here, V of t we can divide, we can get it here, voltage that is hour and some fluctuation part here. And V square is V square equal to AQP plus ACP square plus F. So this is another noise. This F is like basically this is noise. And quantum to signal ratio is that is gamma, that is we can call it here this AQP ACP square plus F. So actually I have done this and I'll just show you here. Here this basically the total, I just put it the short form, but for more detail is it's here. Sorry. Theoretical concept here. This one. So we can discuss this later if you are interested in this. So this is what this is classical phase noise is F, and this is uh, I mean classical and quantum and all these things. So these all these parameters basically we are looking towards to generate the to get this variance part. Okay, so we have just seen the theoretical component, but here we are using this laser, diode laser, in our system. So we are just characterizing this how this our laser is profile looks like and how that so we have this spectrum analyzer. So this one, this is before when we are operating laser at below threshold. So this looks like this, and once we are putting them above threshold, so this is giving you 1 peak here. So this is like after above threshold. So and we also have calculated the variance of laser line width, which is showing like this. This is best fit. Okay, and this approximate for like 70 mode we have calculated here, and this is just to characterize our laser I'm talking about here. So based on that, this laser characteristic, we have operated with this current, and we measure the power here. So this is the threshold, and this is the amplified version of threshold here. So total power is this one, and polarization power we have look at the polarization power and unpolarization power. This is just to characterize. This is nothing else. So to know our system here. So I mean we have calculated this total power, polarization power, unpolarized light power also. Like the same way, we have look at the degree of polarization. So in that degree of polarization, this here we have seen that uh, total polarization and circular polarization and linear polarization. So degree of polarization by using we have some kind of devices for that. So this is the main important part here. That's calculating the variance and SNR. So once we the variance is actually basically that is the output voltage from the photodetector estimated as a function of output power per sampling rate. We are using here sampling rate 10 megasample because due to limitation of our detector bandwidth, and we have found here the goodness fit is like 0.11. So based with the help of this, here this variance formula we have talking about here, this variance formula. Okay, we have calculated this variance here, signal to noise ratio versus power. So this graph is very important here. Okay, so this quantum signal to classical ratio, that is gamma here, that is at 10.6.605 in our system. If you are working on this, it may be different for you. And 10.55 milliamp current corresponding, and the power is like 0.118 milli. So here this is power here. So here this is the highest one, is 10 power 6 6 like that. So at this point here, at this point, if we operate our ledger, then we are going to get maximum quantum signal. This is for the first thing that we have to calculate the operating power of this system here, this system. So I in the beginning I mentioned that this is very important. So once we operate our ledger in such a way that here that laser powers, I mean current should be in such a way that we are going to get power here something like 0 point. So at this signal to noise ratio is the maximum point. So if we operate at this power, that is 0.1 something like that, then we are going to get maximum outcome. So suppose you are doing on this one, so if you do this variance calculation, in your case maybe different if you are using different ledger. So of course that is depend on different types of ledger, and in fact companies also. So once we operated this, uh, you know, we operated our system at this particular operating current, and then we got the outcome, that is a random number, which is basically it's a quantum in nature. And in that case we have calculated the entropy, the way that we have done in earlier slide. I have discussed that how to calculate this entropy. And this is ADC bit. So here for one it's going to be like this is for raw data here, blue one. And once we do the extract after one human entropy is having extractor, so this is increased. So after 2 we are getting nearby, and 3 ADC bit we are getting nearly 3. So means this is useful. If we go for 4 bit, maybe it's less than 4, but not 4. So we have checked this up to 3, and this is giving promising result here that can be used actually. And here this is the autocorrelation. So there's a 3 different types of we have done here for 1 bit ADC, 2 bit ADC, and 3 bit ADC. So what is happening? This is going more towards 0. Okay, this is going more towards 0. Earlier is before a topology hashing, we are getting something like 10 power minus 2, but here now is going like 10 power minus 6, 10 power minus 6, nearly 10 power minus 5 like that. So 1 bit, 2 bit, 3 bit. So this is once is going more towards 0 means is they neighboring point don't have correlation there. And then of course we have calculated the bit rate here. So you can see here the bit rate is here for 3 qubit. So 3 multiplied by 30. So sorry, so we can get up to 30 Mbps. We can go up to Gbps for phase fluctuation, but for that we need at least bandwidth in GB. Okay, not in MB. So detector bandwidth should be high. So we can increase that one. And then we have, because since our detector is not that good for phase fluctuation, so we have done this niche test. And in niche test, what we have seen is that one FFT is not passed. So later on, we have calculated and found that clear all the test. But of course, if your bandwidth detector is low, then this is the problem actually. So we have done this niche test for this phase fluctuation, and except one, all the tests have been clear. This one. There is some ray diagram for different types of generation, QRM generation. Like this is branching path, this is entanglement, this is result feedback, this is phase fluctuation. If you are interested in this, we can discuss more about this one. And here's the application. There's a many real life application like quantum cryptography, online mobile authentication code, captcha, digital signature, cryptography algorithms and protocol, scientific modeling, simulation, seed of encryption key. The multiple application is there for quantum random number generation. And this quantum random number generation is actually, we have seen here, this is based on quantum phenomena. And this is truly unpredictable. No one can predict what is the next outcome. And that's why the future is going to be safe and secure due to this QRNG. Thank you. I would like to have some question, please. And yeah, I would like to show you this one more thing this before going to that. This is Australian National University. They are actually already built this QRNG. So you can go and get directly, if you want to use for some purpose, you can directly use this their quantum random number generation. This is actually, this is the outcome from quantum random number generation. See here. This is the outcome from quantum random number generation. And yeah, you can use this binary form or you can go for color. Okay, this is color. This way also you can use, if you want, you can use some portion of this copy and paste for your purpose. And for hexa also you can see here. This is this is how this random number generated. This random number is basically from quantum source. So it's a quantum random number generation. No one can predict the next outcome. Partially, you can if you want to use from somewhere, you can just stop it and copy it from some person and use for your purpose. Yeah, they have now they have fun stuff also like dice throw and all. So yeah, you can directly explore this Australian quantum random number generation. Yes, please. If is there any question, I will be happy to answer that.
Sir,
Yes, sir. Please, if you have a question, please go ahead.
Participants, any questions? Please ask.
Hello, good evening, sir.
Good evening.
I'm Dr. B. Seshu, Faculty of Physics from KMIT.
Okay.
Um, a very interesting and clear in conceptual understanding from your session. Thank you so much.
Thank you.
What are the experimental facilities that you have shown for this vacuum quadrature and phase fluctuations? Are they available in Hyderabad, in your institution or University of Hyderabad? Because you have shown some experimental results. So,
Yes, yes.
where are the facilities available? I just would like to know more about it.
Okay, okay. So actually, when I was doing PhD in University of Hyderabad, that time we have all these facilities. Okay.
Okay.
This is the question, madam. Should I answer it?
Yes, yes.
Okay. Okay, so when I was doing PhD, that time we had, I work on actually basically quantum communication. So we have all the equipment, detector, laser, and everything.
Yeah.
So I work on BBA34 protocol generated
Mm.
for state of polarization
Okay. Okay.
and did this entire communication. So that time it was clear, and now it's been 10 year after PhD. So and
Mhm.
the department also changed. So
Yeah.
I'm
I know.
not
I'm from
sure.
University of Hyderabad too. Yeah. Okay.
Yeah. So I have to check this with my supervisor. Then if you are
Okay.
interested, definitely I'll talk to him.
Okay. Okay. Okay, sir.
Okay.
Thank you
Yeah.
so much.
Thank
By
you.
the way, in place of half wave plate, can we
Yes.
also use quarter wave plate, which gives us a phase change?
You are talking
The
about
beam
this
splitter.
application, right?
The beam
Here.
splitter.
Yes, yes. No,
Yeah.
no. See, madam, here
Hmm.
we are using this lambda by 2 to
Huh.
suppose what is happening is make it 50-50 beam splitter. Okay.
Yeah.
So ideally, if I'm talking about this 50-50 beam splitter, okay.
Hmm.
So for classical experiment is fine, it will work.
Yeah.
But when we
Okay.
are talking about quantum, when quantum signal involved in this one, then we need more control on that.
Okay.
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 So that's why we are using here lambda by 2. Lambda by 2, what it will do is that it will rotate that,
Yeah.
with some angle,
Yeah.
right? So
Yes. Yes.
to get here equal intensity, I'm talking about here. So we are using here this. So this is one of the. Instead of
Now
that,
my question is, my
yes,
question is, can we have elliptical polarization there? So this is linear or circular polarization, but
yes, yes.
can we have elliptical polarization through this beam splitter and I mean halfway plate, whatever it is?
Yes.
How does that impact?
No, no, see, as per our, no.
Hmm.
See, if you have different types of polarization, then it will not interfere, right?
Okay. So
So,
you need to have only linear polarization, right?
no, no, you can have this both the beam in like in same polarization, either it's linear, elliptical, or circular.
Huh. Yeah.
So, this is why we have done here so much,
This
characterization.
to interfere, right?
Yeah, see here, if you can
Hmm.
see this one, this
Hmm.
total polarization, circular polarization, and linear polarization.
Hmm.
So whatever, see in our system, we have checked here. So whatever polarization means available in this laser. So accordingly,
Yeah.
we
Yeah.
design our system. If it's
Hmm.
a linear polarization, no need, and 50-50, you have a beam splitter, so no need to put all these lambda by 2 and lambda by this is just to make a control over that.
Okay. Thank you so much, sir.
Any queries? Anyone? Yeah, sir. Thank you, sir. On behalf of the Department of CSE and ML, AMIT, and all participants, I extend our heartfelt thanks to Dr. Ram Surat Garu for delivering such an insightful and thought-provoking session on quantum random number generation. Sir, your explanations on the fundamental principles, particularly the aspects of minimum entropy evaluation and QRNG based on phase fluctuation, have greatly enriched our understanding. The clarity with which you presented these complex concepts, supported by practical insights and results, has made this advanced topic both accessible and engaging. We are truly grateful for the time and effort you dedicated, in spite of your busy schedule, to share your knowledge with us. I'm confident that the insights gained today will benefit the participants in their academic, research, and professional endeavors. Thank you once again, sir. Thank you. Thank you for your valuable contribution to this FTP. Thank you, sir.
Thank you, sir. Thank you for giving me this opportunity.
Thank you,
Thank you,
sir.
sir.